Welcome to the presentation of our work on the deployment and scalability of an interdomain multipath routing infrastructure. I am Cyrill, and this work was done in collaboration with Ali, Christelle, Jonghoon and Adrian from ETH Zurich, David from University of Magdeburg and Dominik from Tabaeiaghdaei Systems. It is an exciting time today, given the tremendous amount of innovation we are experiencing. Especially emerging technologies such as virtual reality, holographic imaging and immersive gaming have stringent requirements on the quality of the underlying network that are difficult to achieve in today's internet. Next-generation internet architectures promise to address some of these issues. However, innovators of internet architectures have the same issue as the first developer of fax machines. In essence, who would want to be the first person to invest into a new technology that is used to communicate with others? What was needed back then for fax machine and is needed right now for next-generation internet architecture is a clear deployment plan with tangible benefits for early adopters and an incremental deployment model. The difficulty of deployment is prevalent in many internet technologies, such as IPv6, egress filtering, BGPsec or DNSSEC. Common issues are the lack of incentives for early adopters, requiring additional hardware and software, increased effort or cost, or trade-offs between security and usability. All of these can lead to limited deployment in the real world. In this presentation, we give an overview of the challenges that we encountered on our path towards a next-generation internet. Since I'm from Switzerland, a country that is famous for its mountains, I will use some mountain analogies. As with many internet technologies, the path towards a next-generation internet architecture is steep and hard. In particular, some of the challenges that must be overcome are, when designing a new architecture, it must provide early incentives for ISPs to adopt the architecture. Convincing ISPs to deploy even just a test setup is very challenging, since the biggest motivation for an ISP to deploy the architecture is the fact that other ISPs have deployed it already. The next big step is to have long-term incentives that lead to production deployment. ISPs are understandably reluctant to connect their production network with an untested technology that might impact their core business. Finally, the peak is reached when the architecture is globally available and widely used. The next generation internet architecture we are going to discuss in this talk is SCION. This slide contains the core concepts of SCION. SCION is based on path segments and endpoint path control. SCION's control plane is responsible for routing and its data plane is responsible for packet forwarding. The control plane constructs and disseminates path segments. The process of constructing path segments is called beaconing. On the right side, we have a network consisting of 19 ASs, which are grouped into 3 isolation domains, which offer isolated routing planes. Each isolation domain has a few core ASs, which are shown in a gray background, which provide connectivity between isolation domains. There are 2 types of path segments between core ASs, shown in orange, and path segments between core AS and the non-core AS, in blue and green. The data plane fetches these path segments and combines them to an end-to-end path that can be used to send traffic to any destination. Endpoint path control is enabled by including the desired forwarding path in the SCION packet header. And since the forwarding information is already contained in a packet, routers do not need to maintain a global forwarding table. This makes routers stateless and simple. SCION allows endpoints to know where their traffic is forwarded through, resulting in a more transparent internet. In addition, SCION also allows endpoints to select their packet's path from a set of choices offered by the network. In this example, the client wants to send traffic to the server on the right. There are 2 ways to reach the server. First, over the orange low latency path, which unfortunately has limited bandwidth or high cost. Second, over the blue high bandwidth path, which unfortunately has higher latency. The low latency path might be suitable for video conferencing, and the high bandwidth path might be suitable for applications such as file transfer. SCION provides in-network multipath, which provides benefits to all internet communication. For some people, the term multipath may be synonymous to multi-homing. A typical example of multi-homing is shown on the right, where a smartphone is connected via cellular and a Wi-Fi interface. This provides resilience in case one of the connections deteriorates and potentially improves throughput using MPTCP or MPQuick, which has recently been picked up as a work item by the IETF. However, SCION offers in-network multipath, which provides benefits even if a device is single-homed, and if combined with multi-homing, can give additional benefits. All of this seems difficult to deploy. Let me highlight 2 major challenges that we face. First, there is the chicken and egg problem. We need early adopters to convince ISPs to adopt SCION, but deploying ISPs are needed to convince early adopters. Second, we need to ensure that SCION offers strong long-term incentives to providers, to convince them to invest the resources to update their networks, train their engineers, management, and sales staff. Fortunately, there is good news. As of 2021, 5 ISPs now offer SCION products: Tabaeiaghdaei, Sunrise, Swisscom, Switch, and Telindus. 3 additional ISPs offer pilot services: LGU+, Expo, and Init7. It was a long journey to get to this point, but how did we achieve it? An important property of SCION is that it is federated and thus available on public networks. Any interested ISP can join SCION and benefit from its properties. Also, SCION does not rely on BGP as an underlay, which is an important property to guarantee the stringent performance and security requirements of SCION. An outage due to BGP reconversions or traffic redirections through BGP hijacking thus cannot affect SCION. It was thus not an option to use BGP as an underlay, and the production network does not rely on BGP to provide connectivity. In the beginning, the task seems impossible, since there are numerous hurdles to overcome. The journey of SCION starts in 2009 with the idea of designing a clean slate internet architecture. The design and implementation of SCION went through multiple iterations with different frameworks and platforms, until a stable state was reached, which the current SCION is built upon. In 2016, the first SCION Lab routers were installed in Swisscom, the biggest Swiss ISP, and Switch, the educational ISP of Switzerland. This was achieved thanks to openness to innovation, persistence, and strong technical properties. We consider this step a milestone, since ISPs are typically conservative in the introduction of new technologies that have not undergone extensive real-world testing. When I joined the network security group in 2017, the second big hurdle was already overcome, namely the first actual production traffic was sent over SCION. The first organization that made use of SCION was a national bank, and this deployment had 2 goals: testing the long-term reliability of this new internet architecture and evaluating if SCION could be used to replace their leased lines. The main factor for this deployment was that SCION is not an overlay, but built on a strong foundation and achieves strong security benefits. There were several other deployments during the next part of the journey, but it wasn't until recently that we reached the next milestone. Since 2021, SCION is now offered by ISPs, which shows that the journey for deployment is on the right track. We believe that the main reason for ISPs to offer official products is that they see the business potential of SCION. However, even after reaching this milestone, we still have a way to go until we reach the peak of a global SCION deployment. Tabaeiaghdaei System is a company that offers SCION products, for instance the SCION Transit Service, to connect ISPs via SCION. ISPs can thus leverage native SCION connectivity and benefit from BGP-free routing. There are different ways for customers to deploy and make use of SCION. Here we present some of these approaches. On the left side, we have the scenario where devices are SCION enabled and the SCION components are located at the customer. In the middle, legacy devices send regular IP traffic to a SCION IP gateway, the SIG, which encapsulates the traffic into SCION traffic. And on the right side, we have the same scenario, but with the SIG installed at the provider itself. Internet exchange points are essential in today's ISP ecosystem to interconnect ISPs. In this work, we present 2 IXP deployment scenarios. In the first scenario, an IXP is simply treated as a large layer 2 switch between their customer ASs of the IXP. However, if the IXP is willing to expose its internal structure, it can model individual sites as ASs and thus offer customers additional path control within the IXP. Now that the deployment is advancing, we must think about what happens once we reach our goal of a global SCION deployment. How will SCION scale to a network of infinite magnitude? Network researchers and operators know from experience that as a network grows, its control plane might have difficulties keeping up with the growth. In particular, as more and more ASs join SCION, we must evaluate each of its components and ensure that all components scale to global deployment. We first evaluated the different control plane mechanisms of SCION and then evaluate the scalability through simulations on internet scale topologies. By grouping ASs into ISDs, we isolate the control planes of these ASs and reduce communication overhead. Each ISD has at least one core AS, shown in this figure using the gray background. SCION establishes paths on an AS basis instead of prefix basis, enhancing the scalability of the system. Since SCION border routers do not store any global forwarding tables, there is no need for large TCAMs. Paths can be used as soon as they are disseminated. A SCION border router only forwards traffic and does not need to engage in control plane operations, allowing for simple routers. SCION has two different path segment dissemination algorithms, so beaconing algorithms. The core beaconing algorithm between all core ASs shown using the red arrows, and the intra-ISD beaconing algorithm between core and leaf ASs, shown using the blue arrows. The core beaconing, due to its flooding style algorithm, has the largest impact on the scalability of SCION's control plane. After establishing the connectivity via these two push-based beaconing algorithms, endpoints must look up the created path segments and combine them to end-to-end paths. Here we can see a map of Zurich, where ETH is located. Let's treat each of the yellow breakpoints as an AS and use BGP to find a path from the ETH main building to the beautiful lake of Zurich. BGP would, for example, find the red path as the shortest path. However, if this path is blocked, for example due to construction, then we have to wait until BGP converges to a new path. Compared to BGP, the current beaconing algorithm of SCION finds the BGP path and several alternative paths. However, it does not take into consideration the disjointness of paths and might resend the same path segment multiple times. For example, if either of the last two links of the red path are blocked, neither BGP nor SCION could reach the lake. We improved the resilience of the beaconing by sending path segments with infrequently used links even if they are a bit longer, and we reduced the overhead by minimizing the amount of superfluous routing updates sent. The paper contains more information on the exact algorithm. For our experiments, we evaluate the scalability of SCION and compare it to BGP and BGP-SEC. We extract the BGP routing tables and overhead from the route use dataset, and for SCION and BGP-SEC, since there is no global deployment, we use simulations to evaluate. The topologies used in our simulations are all based on the Krähenbühl AS dataset. This graph shows the control plane overhead of the three protocols as a CDF of the distribution of overheads for different ASs, relative to BGP as a baseline. Note that the x-axis has a logarithmic scale. First, we show that the overhead of BGP-SEC is between 1 and 10 times higher than BGP, due to larger update messages and the lack of prefix aggregation. Next, we look at the SCION simulations. We see that the currently used baseline control plane algorithm of SCION only has roughly 3 times higher overhead than BGP-SEC, while finding up to 60 path segments. However, by applying our novel path diversity beaconing algorithm, we can reduce this overhead by 2 orders of magnitude, resulting in an overhead much lower than BGP, while producing a diverse set of up to 60 path segments between every AS pair. Finally, we see that the intra-ISD beaconing has a negligible overhead, even in a large ISD consisting of over 7,000 ASs, due to the unidirectional beaconing. Since around 60 core path segments and all available intra-ISD path segments are created, an endpoint can combine them to get hundreds of potential end-to-end paths. More information, such as additional case studies on the deployment, a more in-depth explanation of the path diversity aware beaconing, and an extensive evaluation can be found in the paper. To conclude, SCION offers the first BGP-free interdomain multipath architecture that is deployed on public networks. We analyze the scalability of SCION through simulations and find that it is scalable to an internet-wide deployment. Finally, the work on SCION shows that we are not only limited to incremental improvements of the current interdomain architecture, but that innovation in interdomain routing is still possible. Thank you for your attention.